So we'll talk about design consideration of hybrid and electric vehicle propulsion system in electric vehicle. But in the middle of the presentation, I will also talk about the job prospect because those that is the purpose of this of the audience. Most of the audience, I think, who are looking to get into the automotive industry and who works for the automotive industry and how to get prepared for to land in these jobs. So I am Jafri Al Khadri, technical specialist, fuel system safety. I work for GM, as Ashik Bhai told you guys. Um, I come from Bangladesh, and this is my personal information. So I graduated from Bangladesh University of Engineering Technology, BUET. I have twins. They're 8 years old. This is my wife, and she's a doctor. She has been the first responder in COVID-19. So we had some difficult time at the early COVID time. I play cricket. We travel a lot. All the national park in US, I visited 40 of them. Talking about my professional career, I did my PhD from UC Riverside. And I started my career at a power application specific IC designer in a startup company situated in Bangladesh. So after a few years, I came to USA and did my doctorate over there. I started my career in US as a power electronics analysis engineer in GM. I grew up to be a subject matter expert, and now I recently moved from my previous position to fuel cell stack safety. Uh, that's about it. Let's start our main presentation. So when we design an electric vehicle, what are the things we look at? Uh, the first thing we look at is efficiency. It has to be efficient. We need to conserve energy, like whatever energy throughput we put in the car, we better get the best out of it. Meaning that we should have good mileage. We should not have any range anxiety. Once you fully charge the car, you should be able to go as far as possible. Like it should serve most of the purpose. Then cost is a big driver because yes, we want all those good things, but it's not cheap. There's no free lunch. So everything we want to do, we have to engineer it to bring down the cost. There is a thermal consideration because if you are using high power electricity and doing some conversion to do some useful work, byproduct is the thermal energy. So things get hot in any electric operation. If you have used like electronics, like high performance computer, you've seen that how much hot it gets, right? Just like that, if you are doing electrical switching to do the power conversion, there will be some electric thermal energy released, which will increase the temperature of your component, and you better be ready for that. Performance, everybody wants performance. In the old days when electric car just came out, it was very slow and people didn't like it because it took forever for the acceleration. And when you're stopping at a stop sign and somebody on your back is honking you, you'll not be happy, right? So performance was a big push when the electric car came in. Now it is safe to say that electric car in most cases outperforms other cars. So that was a big consideration of electric EV module design, and a lot of things changed from the beginning of electric vehicle to now. So just because the performance was really better, and to increase the performance, a lot of things changed. The way we design the electric car changed, and the whole industry shaped up in a very different way than it was. Then comes the durability and fatigue and warranty. Like if people want a car to be durable, if you buy one car, you don't want to change it every other years. So it better be more durable than your non-electric like IC engine cars. Regulation, there's a big push about regulation, that how electrical, because it's a high power conversion device, and it is possible to blow up even a big like building from the energy that is stored in an electric car battery. So it's a very big battery and very powerful battery. Because it is a very powerful device, it has to be very safe. And whenever it comes to safety, the regulation is also very complicated, and you better be very careful when you design those safety and regulations. Uh, and system specific scenario depends on which kind of vehicle you're designing, and those always dictate your choice of material and choice of design. We'll go one by one in our future slides. Why we are going into electric car? The primary motivation at the point when it came in was environment. You know that how global warming and emissions from IC engine cars is polluting the whole world. And if you do not care about the environment, then it is very hard to convince someone why electric car is better. Yes, there are many other points, but the starting point that, okay, there's something wrong is going on, we better fix it. That's the starting point, that the environment, our mother earth, is getting hurt by the choice that we made 100 years ago, that we will drive car with a gasoline engine. uh, Many of you don't know, like in early days of automotive, when the vehicle, the car, like private car, driving car just came in, was in getting invented. It was electric car that came in first. So people made the right choice at first, that okay, let's make the car electric. But then came in the IC engine. At that point of time and history, that was a way better solution, because electric energy, like the battery was bulky at that time, and the performance of the car did not make economic sense to run a car from electricity, because the range was really poor, and there are all sorts of hazard that had in that period of time. So when the IC engine, internal combustion engine that runs on gasoline, came in, people really loved it, and that was the beginning of the end of the world, I should say. That's a joke. um, IC engine was outperformed electric car by large at that time, and the need for gasoline increased really high, and it shaped up the world politics even, that not every country has the ability to get all the fuel that they need. And we know that over the last 100 years, it has been always the story of fighting for oil, right? So yeah, environment is a big reason. The second reason is freedom from fossil fuel. Like I said, the world politics is shaped up around this fossil fuel um, availability, right? Like even now, because of the Ukraine-Russia war, you know that everything is going up. Gas price in US, you see, is really skyrocketing. People are not happy about it. So we want to be independent of that. So we don't want to be too much dependent on a fossil fuel. Anything goes wrong in the world, that will increase our transportation cost. And we talked about world economy and politics, and long-term efficiency and cost savings. That's the thing. Like IC engine cars, like yes, those were durable, but think about the high-powered vehicle. The cost is really high when you buy it, but those are not like cost effective or long term. They don't have the long term durability. And so if you think about the long term efficiency and cost saving, it makes more sense to go into the electric car than the IC engine cars. So there are long calculation made by many scientists, and we have everybody agrees that, like, for long-term efficiency and cost saving, electric car makes more sense. Of course, the next gen technology is the autonomous driving. We don't want to um, have human driving the car. Why? Because it is already proven that um, autonomous vehicle do the driving way better than human already. It's a bold claim, and it's very hard to swallow, and people don't get nervous to give the control of the vehicle that they're riding on. But think about it, when you are riding on a train or an airplane, how many what percentage of the time human is driving you? Like most of the time human is not. It is a computer that is driving the vehicle, right? Yes, car driving is a very far more complicated scenario, but over the years, autonomous vehicle technology has gone so far that we have less accident reported when the car is driving on an autonomous vehicle, autonomous mode, rather than a human driving it. So yes, the next generation is autonomous driving, and that is for autonomous vehicle. It makes more sense to have an electric car. It's an automatic choice. Connected vehicles are talking to each other. Every vehicle will be connected to the same network, and that way there will be a huge improvement in the sense of vehicle communication. There will be less accident and less chances of error, and also there will be new technology coming in for the connected vehicle, which is a different topic. I'll talk about it later. And there are more services that is possible to add on electric vehicle than you can imagine right now, because it's a game changer. New service economy will come along with the connected and electric vehicle. These are the reasons why electric vehicle is getting more popularity. What kind of electric propulsion we have? If you look into the architecture, that how you are getting the car energy for your car driving, you can have it from internal combustion engine, IC engine, and you can have an assistive power source like regenerative braking that will charge the battery of your car, and if you will have an electric motor, both of them can make the propulsion of your vehicle, and the result is you will have the propulsion on a hybrid basis. It can come from a IC engine, it can come from electric energy. Those are the vehicle we call hybrid electric vehicle. Hybrid electric vehicle does not have the capacity to take the power from the national grid or wall charge. If you add that thing into your vehicle, that becomes a plug-in hybrid, meaning that when you're parking the car in your garage, you're just plugging in your wall, and your battery is getting charged. You can drive around with that charge, with that energy. And battery electric vehicle is completely getting rid of the IC engine, meaning there is no pollution, there is no gas. You're just driving the car out of the battery that you charge at home. So these are the three different propulsion systems that we are using now in electric vehicle world. Let's look at how we came from IC engine to all the way to battery electric. Like long time back, it was called micro hybrid. One example is from General Motors. I'm giving the General Motors example because I work for GM, and I am more familiar with this vehicle. And these are all public domain data, and these are all vehicle that we already sold, and over the time it became popular. So start-stop hybrid is whenever you are starting or stopping the vehicle, um, there are some energy that is not utilized properly, and that is the reason why your efficiency goes down. So stop hybrid technology was something that you are using that scenario when you are starting or stopping the car and converting the energy in an efficient manner. Because when you are starting the car from stall to getting to the first few miles per hour speed, the because of the inertia, you have to spend a lot of energy, and that is when your efficiency is the least. If you can have an assistive power like battery to help the IC engine at that time, the loss can be minimized, and your range of propulsion can be increased tremendously. So that was the start-stop technology. Only battery during the start and stop, this hybrid battery power will kick in. That was a small battery that was there to assist the car in that scenario, and Saturn Vue was an example. And then right after that, we went to e-assist or mild hybrid. The battery got a little bigger, and the voltage went a little up because more power is right now coming in from the battery, and it has a belt assisted system, BAS, assisted system, and that belt battery used to run the motor, and that motor used to run um, uh, the axle or the engine through a belt. So the battery power increased a little. Obviously, the need for internal combustion power went down, and then we moved to hybrid technology. Like it's not only assisting the engine, you can run the whole car either from the battery or from the IC engine. It both is possible. So we were moving from IC engine to battery power. You can see the transition, that as you are increasing the battery power, more and more power coming from the battery, less and less power coming from IC engine. Your engine is getting smaller and battery is getting bigger. So then came the plug-in hybrid. Cadillac CT6 is example of that. Then came the extended range electric vehicle, Chevy Volt. That was a marvel of engineering. It's a very nice car. I had the chance to work on these three cars extensively. And at some point, we decided, okay, that's it. We will go full electric. We removed the IC engine from the vehicle altogether, and the battery electric vehicle Bolt came in. It's a big battery, and the full energy is coming from the battery, and there is no IC engine, no pollution. The next generation is fuel cell electric car. Like you will use hydrogen to convert the use the fuel cell to convert the hydrogen into electricity, and that will give you power for propulsion and charge the battery. Let's talk about the big success that we had, our Chevy Bolt. It was a game changer. Everybody knows about Tesla, the full electric vehicle that revolutionized the whole automotive industry. Chevy Bolt is one of the car that really made a big impact on automotive industry. So it is we'll talk about the propulsion system nitty-gritty stuff in detail a little later. So it had single power inverter module. I was working on this module. So among all the other things, like it had a brand new battery design. It has a very well designed motor, but I was responsible for the power conversion from battery into the motor. So all the high voltage bus, I got the opportunity to work on that extensively. So this is how electric drive system was working, and I will talk about it a little later. Let's talk about the before I go into the hybrid propulsion system. I would like to move the focus to your charging scenario. One of the issue the electric car has is the charging time. There are different levels of charging. If you charge your car at your garage, it will take forever to have the full charge and full range. You see the power is really low if you do it in garage. In USA it is only 110 volt. In Europe and Bangladesh it's 220, but it's still it takes at least 3.5 hour to get sizable amount of range. Then if you move up to level 240, if you use a three-phase in your garage and have a bigger like a charging facility up to 7.2 kilowatt, it's again up to 18 mile per hour. It's not very much. Level 2 is a charging station. If you go to the dealership and charge your car through AC, which is 3.2 to 19.2 kilowatts, it takes 8 to 49 minutes per hour. Miles per hour, sorry. If you go to the DC fast charging, which like many car industry introduced, and it's a really fast charge. It charges your car in really short time. Like in 30 minutes, you'll have 80% of the charge. It will give you 570 mile per hour charge if you are charging using the DC fast charger. So why we are talking about this charging scenario? Because like if you are running an IC engine car and you ran out of gas, what you do? You just um, stop by a gas station and like fill up your tank in 5 minutes. And that's not true for electric car. It takes forever to charge. So you saw that, like if you are charging in garage, like it may take you it's very really slow. It may take you like 8 to 10 hours for overnight charge, just to charge up your entire battery. So not many people will have the luxury to go into these different levels of charging, and that is why people avoid the electric vehicle, even though it has a lot of good reason to buy. So we because this we have a pitfall over here. There is a need for design the whole system in a way that even with certain pitfalls and certain shortcomings, you are you are designing the vehicle in a way that people will still want to buy it. And automotive system engineering is not a very easy thing to do. Like if you are changing the whole power source of the vehicle, and that will require a lot of different consideration in your system. So if you're talking about automotive system engineering, it has been developed for last 120 years. Like there is a lot of different things you need to think about while designing a vehicle. And it's a highly cost driven industry. Like if your vehicle costs more than your competitor, nobody will buy your one. And there is a lot of competitors, and the market is really competitive, and the profit margin is not very high. We make money from the volume, because a lot of car is sold and bought every year. So because of this highly competitive market and safety and regulation, the automotive industry is very I should say very fragile. Like if you want to change one thing, it impacts so many other things. It's interconnected. So it is not very easy to introduce a new concept into this industry, and that's why it's taking a long time. Think about other tech industry. It doesn't take a long time for a concept to materialize. For auto industry, it is taking a long time, and it is the case all the time. um, if you're talking about commercial vehicle, it's even more complex, because the regulation is a huge thing, and also the long-term efficiency and cost that I talked in earlier slide. Um, there are things, expectation that is getting increased from electric vehicle is people want very good software in EVs, and good and durable electronics that will last for years. It is expected that if you buy a phone and it stops working after a couple of years, people don't mind that they just change the phone. But if you buy a vehicle, you don't want to change it every 2 years, right? It better be 5 years at least. And it's preferable to last for 10 years. And the a high power machinery that you're using every day, and doing a power conversion of high scale, it is very difficult to make it durable. And that's why the engineering constraint is so high in EV manufacturing. Now, to facilitate the EV, we are trying to change the infrastructure that will be supporting the advanced mobility services, the smart cities that will have wireless vehicle charging under the road, all you need to do, you just drive the car. There will be inductive charging facility under the lane of a road, and your car will get charged inductively, wirelessly when you're driving it. Just like a toll lane, you'll pay some toll for your car charging. So that is also an engineering and development, very interesting. If you're talking about system engineering, this is not let's think about it. If you want to make an electric car, like what is the process that you will make it? So we call in system engineering process a V curve. So we define the concept and we build the product at the end. It's a long process. What is the process that we follow here? We do the requirement analysis. When we first define the car, we do the requirement analysis and of every component, like what it will do, how far it will go, how big it will be, how it will look like, what will be the capacity. All those things we think about, and we capture it in a requirement, and we analyze the interaction between the components, and then we do the functional analysis, that okay, if these components do this kind of function, what how it will be interacting with each other, and like is it possible to meet the scenario or criteria that we are putting in, the number that we are talking about? Is it possible to do that kind of have that kind of mileage? Is it possible to carry that kind of weight? Is it possible to have that kind of acceleration? All those things. Then from functional analysis, we move to functional synthesis. So every component is analyzed and defined. We synthesize together to come up with the system. Then we do the component analysis and design. Like after functional analysis and synthesis is done, each individual component is analyzed and designed, and that is where the engineering effort starts, especially for EV. This curve is pretty generic, and it applies to many different kind of product development. But for EV, I can tell you the component analysis and design, this is one of the big like engineering effort that is required in this phase. And then we the component implement we go to the some of the component we design ourselves. Most of the component the automakers buy from other component makers or suppliers. They go to the supplier and purchase those components, and they implement it and like put them together and start the testing. It is not possible to test every component physically, so we do some virtual subsystem integration and test it that way. After virtual testing is done and we are satisfied that okay, components are working independently, very nice, let's go into the physical system and integrate all the component together and do the testing. And after the system is integrated, we do the testing at the vehicle level. And after the test is successful, that okay, whatever we designed in the beginning, whatever we thought that we will be doing, this is after the test we saw that this is exactly what was envisioned. Then we accept that okay, the product is satisfactory, and we go for sell. The whole aspect of system engineering is a very complex and multi functional or multi I should say different kinds of engineers comes together, and multidiscipline research and development process happens here. So same curve, this is put together in a slightly different perspective, that what auto industry do for system engineering. So we do the concept design, and we do the design charter, we do the subsystem technical specification in powertrain. We do the powertrain specification. Then initially we do the spec. Then we do the system breakdown in the spec, that okay, this is our system and this is the breakdown for each of the system. Then now let's go and shop around for supplier who makes this kind of part that will fulfill the purpose. And we complete all the subsystem specification, go to the supplier and shop around. We call this process sourcing. We build the car, and some of the part we build ourselves, some of the part is sourced out means sourcing, and we purchase them. And after we get all the component together, we collect them and interconnect them, and the functionality is checked. The software is written there at this time. We do the testing after we put together all the materials, and we do the design validation and production validation. And at the end phase, we do the vehicle level validation and final calibration. After everything is satisfied, we say it's finally okay, uh, okay to sell. So this whole thing used to take 5 years. Okay, now the whole thing is now squeezed into 2 years. There is a interesting thing going on. Before Tesla came into the picture, the whole auto industry was used to that this system will take a long time. But now we are more into like, can we make it faster? And the whole thing is squeezed into 2 years now. So who works for EV engineering and development? We have electrification in all power level. We have power conversion, high, mid, and low power. We have, and so electrical engineer is needed in every power conversion and system integration level. We need mechanical engineers because of the implementation, packaging, thermal, and mechanical. After all, car is a mechanical device, right? Let's face it, it is a mechanical product. Even though it's electric vehicle, it is a mechanical product. So we need a lot of mechanical engineers. So chemical engineers also work for us, like battery electronics, battery material, the research and development needs a lot of chemical background engineers to work for them. We need material scientists, same reason, but there are more into it, like not only the battery, each part of the battery, each part of the vehicle needs different efficient engineering for reduction of cost and durability and increase the efficiency. So composite material research is a very important and very popular thing in automotive industry. Data scientists, oh my gosh, who is not data scientist now? Everybody is data scientist, right? so so we use data science extensively in every aspect of engineering. So from initial concept development to machine learning to like purchasing to selling the car and to the market analysis, everywhere data scientist is needed. So like the whole tech industry is I should say revolutionized by data science. We are also not an exception. We also use data science extensively in every aspect. Computer architecture and security, because the vehicles are connected now, and autonomous vehicle is now coming more and more. There is a huge push for computer scientists to capture all those regulations and futuristic concept into our vehicle, like things like algorithm architecture, cybersecurity, human computer interface, um, microprocessors, AI, you name it. All the branches of computer science is used now in the automotive industry. We also need civil engineers. We talked about the smart charging infrastructure and smart grid system. Like, if there are millions of cars sold, do you think our grid is ready to support all the power needed for this kind of car charging? I don't think so. So we need to upgrade our grid system pretty soon, and there is a need for infrastructural development for charging station. So civil engineering, civil engineers are needed for those kind of activity. There are separate department to look into those, and this goes on. Uh, this is the section of my presentation. I'm trying to give an insight to the audience that who are trying to look for a job in this industry. What kind of engineer we hire in automotive industry? We hire design engineer, test engineer, validation, release, software, data engineer, integration engineer, performance, product. Like the list goes on. I just put together whatever came into my mind. Like I can assure you, there are 30 to 40 different kinds of engineer we need. There are more jobs in this industry right now than there are qualified people. So the what kind of skills are needed for to land in this kind of job? These are the skills we can think about. You need to be technical expert. You have to have technical depth and knowledge, analytical and problem solving, all sorts of things. Like I will talk about this aspect a little later, but this is a nice way to summarize like why auto industry needs a lot of engineers and a lot of different skill set right now. So you better be preparing yourself to land in those job opportunity. Prepare yourself, make sure you're competent enough, be good at what you do and what is expected in the job description. Do not just keep applying because there is a job posting and you saw that. Irrelevant job application will reduce your chance only. Behavior is a very important thing. Prepare yourself for correct behavior for the interview, and you can take preparation. There are tons of material in the internet. You can really take good preparation based on those. Make outreach and build your strong network, and that will give you more chances to land in this job those jobs. Be creative to pitch yourself to fit into remote jobs, and you will be amazed to know how many remote jobs are there right now. So you don't have to move state, you don't have to change location apply for the remote job, and I think that's a good way to start your career. And I know some success story in last couple of years. There are more remote jobs than there are physical jobs here. And be flexible, be accommodating, and learn new skills like generic skill like writing Python script and having working knowledge on data science and scaled agile framework. Those are very popular and up-to-date knowledge. I think those are the things that people look for. Uh, Prepare yourself for STAR method for interview. If you look online for what is STAR method for interview, you will get a lot of material, and prepare yourself for that kind of interview. If you are not familiar with that format, I think it will be hard for you to crack the interview, because auto industry like in auto industry, STAR method is very popular, and a lot of big names follow this method. So it's nothing like they will ask you a question and you'll answer it in four different bullet point way. Like they will ask, you'll describe a situation, then you will for that particular situation, what is the task you are assigned to, and upon assigned task, what are the action you took, and what is the result you got based on this scenario. Like prepare personal stories in star format for interview, and that will really help you. Now let's go back to our original discussion. I just moved away from our original discussion of design consideration of EV. I just put together a couple of slides so that the audience can get some benefit and to understand the job scenario that's going on right now in the automotive industry. So if you look into the EV architecture, there are the classification of series parallel hybrid and like series parallel hybrid or fuel cell hybrid. No matter how it is classified, the crux of the matter is how you are getting the energy into the wheel of your car, how your wheel is moving. If your wheel is moving purely from electric energy, it is EV, right? But if you are using also a IC engine and taking energy from petrol, then it is a hybrid, right? You're uh, getting energy from electric energy and chemical energy, right? It can be mounted into your motor in through a converter in series manner or in parallel. So that is why the nomenclature came in series hybrid or parallel hybrid. If you are something like this, sometimes it is going this way, the flow of energy is like this. It's called a series parallel hybrid, because the petrol is running an engine, and the engine is running a generator, and generator is connected to the converter. Same way as the series hybrid, but the difference is your engine is no longer directly connected to the shaft. So it can be series hybrid, parallel hybrid, series parallel hybrid, or if you have another kind of energy like hydrogen, it can be fuel cell hybrid. So no matter how you are designing it, keep in mind in every aspect there should be some power conversion happening in either from mechanical to chemical to electrical, and from electrical energy is it AC to DC or DC to DC or DC to AC, there will be power conversion, and that is where the need for engineers comes in. uh, if you are talking about the BESS system, battery electric system, there are major components in there. Uh, so there are, see, not only the motor that is going into the vehicle, there are some other components also needed for the successful propulsion. So right now I'm showing a typical example of what are the components that goes into the electric cars. Each component has particular function into the functionality in an electric vehicle. Like you see the part TPM is this is an inverter that is running the motor and that runs the wheel. But not only that, battery to inverter to motor, it's not that simple. The objective of this diagram is to let you understand that there are more into electric vehicles than just from battery to motor propulsion. There are other components that is also using the battery, and these needs a lot of different engineering skill to integrate. Like there are AC compressor, there are cabin heater, there are charger, there are accessory power module. Each of them are integral part of a BEV system, and that is why the need for engineering knowledge and skills is skyrocketing in this industry. There are all kinds of power conversion happens in all the modules that I just showed you. There are DC to AC conversion, there are DC to DC conversion, and in all this kind of conversion, and I am also putting some names that what are the conversion called. There are power losses, and that will in fact reduce your range. At the end of the day, because of the power conversion, there will be thermal energy released and increase in temperature, and that is where the need for engineering comes in. Need for modeling. So for this kind of conversion, there is a need for modeling. So there is a term that you will soon hear more and more. It's called software defined vehicle. All those things that we have been making cars for 120 years, and in the olden days, what we did, we build a model and then tested it. As more and more computer technology developed and modeling matured, now what we do is we make a software model and do the testing in the model. And the software is and the model is good enough to give us a very high fidelity data. And that's why less and less hardware development is going on, more and more software development. We are relying on more software to make these predictions. So in developing hardware and integrating vehicle and testing, validating makes EV development very complicated. Like each of the phases, you are moving away from the status quo, which was hardware test development and testing, into more and more software dependent scenario. This makes like the validity of those software models are being questioned. And now, as we are maturing in this industry, uh, the better models are coming along, and it takes less time to do the things in softwares. And that's why remember I said that it takes 5 years to make a vehicle. It was, and after Tesla, now it is 2 years. And this push in reduction of vehicle development came from the software defined vehicle philosophy. So there are efficiency concerns in power conversion. As I said, there are power conversion AC to DC, DC to AC in every aspect of electric vehicle. whenever you are doing, there are some fixed loss, switching loss, and conduction loss going on. Every time you input some power and convert it to a different kinds of energy, whether it is AC to DC or DC to DC, or mechanical to AC, it's always there are some losses, and you have to estimate that losses, because those losses will reduce your propulsion range and the overall efficiency of the vehicle. So if you look into hardware example, if you open an electric vehicle, there will be converters like power converters. This is one power converter. I'm just showing. I took it from one of my colleague. It's a full bridge converter. This is a public domain information, because it's not a very. It's an old vehicle that I'm showing. Um, there are switches, electronic switches that we use, and the primary switches that we use here. You can see the switches there. IGBTs right now are using our MOSFET. There are secondary full bridge converters and secondary level switches, which are even bigger in current rating and lowering voltage rating. So you can see the transformer that is on the board. So the objective of these slides is showing you an hardware example. All those things that we study in engineering school, that what is the transformer, and how we design the transformer core, and how we design the turn ratio, how to do the math. All of this comes into play in electric vehicle, and we do it every day in every component that you can imagine. So all the output in input capacitance that you are seeing here, these are all part of power conversion that we talked about. If you look, for example, if you look into the Toyota Prius, it's a pretty old car right now. This has been for years. They also have the power converter boost conversion, and they have the IGBTs. If you look into an Infineon power module, they have IGBT and diodes. All this power electronics component that you learn in school is extensively used here. And to estimate the efficiency and conversion scenario, you have to make a good model of that, and that requires a lot of engineering understanding and model development. Uh, for example, if you this is one of the work we did, my group did actually. So say if you're trying to model the IGBT and diode in here, so how the switching characteristics goes on, how it will behave in certain kind of voltage and current switching. So we had to build characterize the MOSFET and predict the curve, that how the DIDT, DVDT, E-on, E-off, and gate resistance, all the characteristics will go on. We have to design the design the um, circuit boards that will dictate the efficiency and meet our goal of power conversion. I intentionally put some blanket on the numbers, because I thought that this is something should not be public anyway. So this is just to show you how things are developed. Like we characterize the sometimes we buy component from suppliers and characterize them and integrate them together to predict and design how it will behave into our system. Of course, the supplier has some data sheet, and they do provide us the characteristics of the component, but how it will behave in our system is something different. I think we are running out of time. I will go through them quickly. There are other things that we also mm, characterize the power module. Even the cable that you see, is connecting the battery into the power component. We also model them extensively, so that each of the things that you model, it is modeled very carefully using the math, thermally and electrically. Uh, we also do the modeling for electromagnetic emissions, and there are some regulations that you have to follow to be able to sell the car. We do the EMC modeling for that the FCC requires us to do before selling the car, and we use different kinds of tools to do our modeling and predict that we meet our spec. End of the day, power electronics component design and decisions are driven by battery and motors design of the vehicle, and there are performance criteria of these components. The EV is a very multidisciplinary engineering application, I should say, because I have worked with chemical engineers, mechanical engineers, and electrical engineers, needless to say, computer engineers and data scientists over last 10 years. And I have seen that each of those knowledge has application in this EV manufacturing and development. So if you are looking into getting into this auto industry, I think this is a very good time to get into here, and there are multiple jobs available right now. I think we are almost done. I'm 5 minutes over. Sorry for that.
No, you're okay. Thanks for the nice presentation. So we have one question, couple of questions actually from the audience. So we'll go through those first. So Salah is asking, is there any data to compare how much pollution and waste created by battery industries versus created by IC engine vehicles?
Well, yes, there is data, and there is a comparison made for how much pollution this battery industry is making. There are two things I need to say. Number one, yes, battery manufacturing is a polluting process, and there is no doubt about it, but it is confined, it is not distributed. What happens for the car, for the electric vehicle, it is distributed pollution. You are driving the car and you are polluting our mother nature as you are driving. So it is impacting the nature in every different corner. Whereas if you have a battery manufacturing plant, it is easy to contain the pollution in one place. That is the number one scenario. Number two, yes, if you put some number, there are less battery manufacturing plant in the world than there are IC engine pollution. Of course, the number is favoring the battery vehicle, but that is not a fair comparison, and I do not have at this point on top of my head the exact data. But I can tell you that there are reasons why this distributed pollution is really hard to control, and the favor for electric vehicle is stressed more and more, even after knowing that the battery manufacturing is a polluting business.
Okay. All right, second question from Ejazul Haq Shobuj. Can you please discuss a little bit about the battery management system, especially voltage and thermal management? I know probably we don't have enough time to talk about it, but briefly.
So battery management system, yeah, I can, like I had limited exposure on battery management system. There are few things in battery management system. One is cell balancing. So each battery is created using hundreds of cells in series, right? And of course, if you are using the battery for high capacity or high current, you'll do in few strings in parallel. But each of the battery is like, you have say 300 battery in series to make some bus voltage. But are they, when you are charging, are they charging equally? No. What happens because of the chemical scenario, the cell, all the cells are not charged equally. Some of the cells may charge more than the others, and that becomes the bottleneck of the entire bus voltage. So there is a clever way to balance the cells in a way that all the cells are equally charged, and that is a major part of the battery management system. Cell balancing. There are active balancing and passive balancing. There are thermal management. So you need to performance of a battery for charging and propulsion varies a lot due to temperature. So there is a thermal aspect of the battery management system that you need to keep the temperature as favorable as possible. So there is a battery heater, there is cell balancing, there is thermal management, and also there are current and voltage monitoring at the stack level. So all of these variable that the battery is providing you, you need to keep a very good trace on that, because you cannot exceed the limit of the cells that you engineered for. Because if you are failing, think about a battery string. If one of the string is not working, you're losing the propulsion and you are losing the capacity by a lot. So it's a very very sensitive part of the electric propulsion, and that it's a continuous process that battery management system will keep an eye on all the critical variable that is required for the health of the battery.
Okay. So we'll have time for 2 more questions. We're a little over time, but that's fine.
Go ahead.
So good question from Ajim Bhai. A common question is battery charging. We'll be using electricity to charge the battery, and the source of electricity generation is still from fossil fuels. Any comments on that?
Yes. So there are two terms I need to use: well to wall and wall to wheel. Well to wall means you have the fossil fuel under the mine. It's a well. From the mine, you dig up the fossil fuel, do the conversion, produce the electricity, and supply that electricity to the wall. So well to wall. Then wall to wheel. You take the energy from the wall and use it in your charge the battery of electric car and drive the wheel. So this is, no matter what you do, well to wall will be there for producing electricity, and that will be generating some pollution. The wall to wheel part is the one that is in question. That if you were using IC engine, what will be your total pollution versus well to wall plus wall to wheel? It is much easier to control the pollution of well to wall. Yes, wall to wheel, we can come up with better engineering to reduce that part, but still well to wall, that part is there, and that is why electric car is being criticized. As more and more technology is progressing, well to wall does not have to be always well to wall. It can be sun to wall, it can be wind to wall. So that is how I'm going to answer it right now. There is a long discussion happening on this topic, and I think it is pretty much the scientific community is on the same agreement that still we know that that part of pollution, after considering that, electric car still makes sense. I hope I could answer.
Yeah, good answer. Last question, and we'll end with that. So question from Ashik Yusuf Bhai: how is the fuel cell technology going to help the industry?
So I moved into this fuel cell group in last January. This is my new job. I'm still learning. So let me tell you one thing. How you gonna change all the grid system that will be needed to upgrade to support the additional power that you will need to charge your electric car? It's a huge cost, and some of the grid system that we have is 100 years old, right? Like most of the country is not really agreeing to do that, and they're reluctant to do the cost. So if how many gas station you have in US? Like millions, few millions easily, right? Those gas station will have to provide fast electric car charging, right? Is it possible to build that huge infrastructure that all the gas station will have the electric car charging facility. No, it's not possible. It's not viable, or it's not a very good way of solving the problem. Like it's a bummer. That is where the fuel cell can help you. We are trying to build a power cube, which is we already have generation 2. I'm building generation 3, that will convert the hydrogen into high power electricity generation module. So when the oil pump will get the fuel from their supply, they will also get hydrogen from their supply, and those hydrogen will power up the power cube and fuel cell power cube, and that will convert the hydrogen into electricity that will charge the electric car. And that way you can like convert all those millions of gas station into car charging station. And that's, we are envisioning it will be a big market.
Thank you so much for the explanation. Appreciate it.
Thank you.
Okay, we are at the end of our today's webinar. Thank you, Jafri bhai, again very much for the nice presentation, and thank you everyone else for joining. Hopefully we'll see you all again in our third webinar next month. Thank you all.
Bye bye.
Bye bye.